Welcome to today's Explainer. I am absolutely thrilled to be your host for this one. We're going to take a deep structural dive into one of the most talked about, yet, let's be honest, frequently misunderstood foundational elements of our biology. Yep, we're talking about carbohydrates. Think of this as a mini lecture that connects the microscopic chemistry happening at the molecular level directly to your whole body health, your energy, and your metabolism. We're going to break down these complex biochemical concepts and make the actual foundations of our biology crystal clear. Here's our roadmap for today's masterclass. First, we'll start by meeting the hydrates of carbon. Then we'll explore how simple sugars shapeshift and see how the body builds complex carbohydrate chains. After that, we'll look at glucose as our primary fuel. And finally, we'll tackle how fructose and excess carbs impact our long-term health.
All right, let's jump right into section 1. Meet the hydrates of carbon. We really need to nail down the academic foundation before we can dive into the broader physiological effects. To truly grasp what a carbohydrate is, you just have to look at the name itself. They are naturally occurring organic compounds that act as our major energy sources, sure. But listen to the literal definition, hydrates of carbon. Chemically speaking, they're polyhydroxyaldehydes or ketones, and their general formula is CnH2O(Y). Basically, for every carbon atom, you generally have the equivalent of a water molecule attached right to it. It's just a beautiful, elegant piece of natural engineering. So where exactly do we find these hydrates of carbon? Well, it's definitely not just in the bread or the pasta on your plate. They're incredibly diverse. Obviously, yes, they're found in sugars, starches, and cellulose, but they're also structural. They are literally built into bacterial cell walls. And amazingly, they even form those tough insect exoskeletons you see on beetles. Now, when we break these down to their most fundamental, simplest forms, the ones that literally cannot be hydrolyzed any further into simpler compounds, we get what are called monosaccharides. And they come in a bunch of different sizes, ranging from 3 carbon atoms, which we call a triose, all the way up to 7. That brings us to section 2, shape-shifting simple sugars. This is where the chemistry gets remarkably dynamic. Simple sugars, or those monosaccharides we just talked about, are classified by their functional groups. An aldose, like glucose, features an aldehydic group. A ketose, on the other hand, like fructose, relies on a ketonic group. Now, I know that sounds like a super subtle structural difference, but as we'll see a bit later in the explainer, this tiny distinction has absolutely massive implications for how our bodies actually process them. And what's truly wild is the dynamic nature of these molecules. A molecule of glucose doesn't just sit there rigidly. It can actually interconvert from an open linear chain, folding in on itself to become a closed cyclic ring. These monosaccharides are literal shapeshifters, constantly transitioning between linear and cyclic structures depending entirely on their environment. So what dictates the shape they take? Well, stability. Sugars with 5 carbon atoms, pentoses, or 6 carbon atoms, hexoses, are actually way more stable and therefore way more abundant as cyclic rings rather than open chains. Specifically, fructose forms a 5-membered ring called furanose, while glucose forms a 6-membered ring known as pyranose. And there's a really fascinating rule of thumb here. In their pure, solid state, these sugars exist in their ring form, but the second you dissolve them into a solution, they open right up and exist as linear structures. Let's bring this abstract chemistry into the real world for a second. Think about a jar of honey. Why is it so incredibly thick and sticky? It's because honey contains really high concentrations of fructose and glucose. Both of these simple sugars are just covered in hydroxyl, or OH groups. And these hydroxyl groups form extensive, incredibly strong hydrogen bonds with one another. That microscopic molecular grip between the sugars, that is exactly what creates the heavy, gooey viscosity of the honey you're drizzling on your oatmeal. Okay, let's move on to section 3, building complex carbohydrate chains, and see how this all builds into much larger, intricate structures. Watch how this chemistry scales up by taking those simple pyranose rings we were just looking at and linking them together, specifically through what are called 1,4-glycosidic linkages. Nature creates these vast, complex polymers. This is exactly how we get the intricate architectures of amylose and amylopectin found in starch, alongside cellulose. Just by repeating these bonds, structural differences dictate whether a carbohydrate is going to act as a rapidly digested starch or a really tough, indigestible structural fiber like cellulose. Now, let's shift our lecture away from pure chemistry and into human biology with section 4, glucose, the body's primary fuel. The crucial point here comes down to raw power, 15.6 kilojoules. Simple sugars like glucose are the primary, most easily absorbed source of energy for our cells. When just 1 single gram of glucose is metabolized by your body, it releases a massive 15.6 kilojoules of energy. It is an incredibly efficient, highly dense biological fuel source that keeps your entire system running. Because glucose is so powerful, it requires exact management. A healthy, normal blood glucose level ranges between 70 and 110 milligrams per deciliter. It fluctuates a bit during the day, sure, but it is masterfully controlled by the hormones insulin and glucagon. However, if blood glucose levels rise above this normal range, maybe because the pancreas isn't producing enough insulin or the body just can't use it effectively, it leads to diabetes. This uncontrolled hyperglycemia causes massive macroscopic damage over time, severely injuring nerves and blood vessels across all of your body's systems. But what happens when things are working correctly? Honestly, your body is brilliant. Excess glucose isn't wasted. It's efficiently and quickly packed away, stored as glycogen in your liver and muscles for later use. Balance really is the key here. If you have insufficient carbohydrate intake, the result is this deep, draining fatigue and a stark drop in both physical and mental performance. On the flip side, having sufficient carbohydrates is highly protective. When the body has enough carbs for its energy needs, it uses those first, and that spares your crucial proteins and fats from being desperately broken down for fuel. Which brings us to our final topic today, Section 5, fructose, excess, and health. Here, we're going to address how different types of sugar intakes actually dictate our long-term health outcomes. We talked a little earlier about fructose, that ketose sugar found heavily in honey and fruit. The main function of fructose is indeed to provide energy during metabolism. However, the dose makes the poison, right? High intake of fructose, particularly from modern, highly processed diets, causes an excessive accumulation of fat in the body, which can result in obesity. Diets high in refined sugars are strongly associated with much higher risks of chronic conditions like diabetes, heart disease, and even certain cancers. Conversely, complex carbohydrates and fibers, those intricately linked chains we saw earlier, are highly protective and offer multiple health benefits. The type of carbohydrate you choose fundamentally alters its physiological function in your body. We've journeyed all the way from the microscopic definition of a hydrate of carbon, right up to the macro realities of chronic disease and health. So I want to leave you with this question. Since complex carbohydrates protect our health, while excess simple sugars drive disease, how does understanding these microscopic, shape-shifting structures change your view of your own physiological destiny? The next time you look at a plate of food, you won't just see a meal. You're going to see the 1,4 glycosidic linkages, the cyclic pyranose rings, and the biological fuel that literally drives your existence. Thank you so much for joining me in this explainer, and keep exploring the incredible chemistry of your world.